Well, welcome to part 1 of 2 of Introduction to Orbital Mechanics, and thanks to the folks from AGI and Project Lead the Way for providing us with this material. Well, so what is an orbit? Anyway, an orbit is really just, as you see here, it's a closed path around a planet that a satellite takes. And a satellite, by the way, could be natural or man-made. So, for example, the space station is a man-made satellite, but the moon is also considered a satellite. One thing to notice or to note that's important is that some people kind of get the word trajectory and orbit confused. So an orbit is generally a closed path. We'll find later that there are different kinds of orbits. We're going to focus mostly on ellipses because those are the paths around the Earth that we're most interested in. Johann Kepler was one of the first to discover in the 1600s that the planets circled not in they orbited not in circles, but in ellipses. And one of the amazing things is that he observed that with his naked eye. He didn't have any special equipment. He didn't have any computers. And I think that's pretty amazing. And he came up with several laws that we'll talk about later in part 2. But he really made some observations based on some earlier work from Nicholas Copernicus. So to understand orbits, we need to really understand what is an ellipse and kind of break that down a little bit. So you probably remember from math when you studied conic sections in algebra, if you look at a circular base of a cone, or you look at a circular cone, that's where conic sections come from. And an ellipse is really just the shape. If you were to take a plane and cut that cone at any angle that's not parallel to the base, and you pull that top off and look at it flat, it is an ellipse. And we can look at an ellipse and we can make some definitions and distinctions. Well, a circle, first of all, let's compare a circle and an ellipse. So a circle is really just a special case of an ellipse. So a circle is where the two foci of an ellipse, which are shown below in the bottom, A and B are their foci or focus points. A circle is where they're just both together at the same time. So the interesting thing about an ellipse is that the sum of the distances from the focus or the foci to any point on the ellipse, and here you can see two segments, segment A and B. If you were to have that, measure those distances to any point, the sum of those two are constant. So let's take a little closer look and make some definitions here. So here you see a traditional mathematical definition of an ellipse. And so you have two focal points, F1 and F2, and the long part, if you will, so it kind of looks like an egg. The long part from end to end is called the major axis. And from half of that, so C, from point C to the longest point, is called the semi-major axis, and we call that A. So note from the diagram, it says 2A is the major axis. So we call A the semi-major axis, and we call B the distance from C, from the center, to the shortest side, if you will, the nearest point. That's the minor axis, and half of that is the semi-minor axis. So again, just note that for a circle, A and B are the same. One thing about orbits, if you take a look at the focal points, and we talk about an orbit around, say, Earth, Earth would be at one of the focal points, and the other focal point will essentially be empty. Let's take a look at some different kinds of orbits, and let's watch this video. I'm going to let this play out, but we're going to talk a little bit more about these different kinds of videos. And as it rotates, you see the green video. The dot represents a satellite. It's going slow. It's farther out, and we'll talk about why. The pink represents a special, highly elliptical orbit. Then there is also a high inclination orbit and a lower Earth orbit. So this is a little bit longer video, and as it plays, I'm going to describe a little bit about each of these. So there's LEO, or LEO, which stands for low Earth orbit. You'll need to know that. MEO is medium Earth orbit. HEO, high Earth orbit. And then GEO is basically a geosynchronous orbit. This is a little bit longer video, and so it takes a segment and it focuses on each of these. So here you can see the green dot, which represents low Earth orbit. And the different kinds of low Earth orbits. So, for example, the blue one there where it says radar sat, it has what we're going to learn is a different inclination. It's flying over the North Pole and South Pole. And so is the pink version there, the Iconos. And we'll learn about why you might have different kinds of orbits like that. One might be synchronized with the sun to follow the sun. Another might be looking strictly at the poles for a specific reason. MEO is medium Earth orbit, an application that you know of and you use probably quite often if you travel a lot or drive, are GPS. So GPS, and here you can see sort of the constellation and how GPS satellites all communicate with each other, but then they also communicate with a geosynchronous satellite so that they can all communicate with each other. And notice the geosynchronous satellite is the purple that's orbiting, and it's going to the backside of the Earth right now. The farther away you go, and we'll learn this in a future slide, the farther away you are from the focal point, the slower your orbit is going to go. This is a highly elliptical orbit, and it's called a Molniya orbit. And this is typically used for northern countries. Think Canada, think Russia. You know, here in the United States, we're in medium latitude. So if we were to launch, say, a satellite from the coast of California and use it to view a lot of the United States, you can't do that from, if you want to observe Russia, you have to have something go a lot farther north. So we'll learn a little bit more about these special orbits as well. Notice how it goes faster when it gets closer to the South Pole, and then it slows down. And finally, you see here the GEO. It says GEO, it's geosynchronous orbit or geostationary orbit, and that follows the sun. So if we were able to see one of those at night, which you can't with the naked eye, but it looks like it's parked right over the equator. So its period, or the time it takes to rotate about the Earth, matches the Earth's rotation. So it's 24 hours, actually it's 23 hours and 56 minutes, but they're used for communication satellites. And here you see how it can communicate with low Earth orbiting satellites in a constellation. So regardless of where that low Earth orbit satellite is, it can find a geosynchronous satellite to communicate with. So how do we describe orbits? So we've seen some really cool videos of what some different orbits are, but why do we have different orbits, and how do you describe them? How do you define them? So we know that they're in ellipses, but how do you define the shape? How do you describe one to another engineer or scientist? Well, there are basically 6 elements. We call them Keplerian, elements, and every type of orbit has all 6. Plus, you have to have a timestamp. You have to tell the other person that you're communicating with when you took those measurements. So let's take a look. So first of all, let's go back to the ellipse. So one of the things that is important is eccentricity. So really, that's how oblong or how egg-shaped, for lack of a better expression, is that ellipse. So eccentricity is just simply E. There's no Greek symbol for it. It's just E. There's the formula for it. So if you were given the semi-minor and semi-major axis, or for that matter, the minor axis or the major axis, you can find the eccentricity. And for eccentricities between 0, not including 0, 0 is a special case that is a circle. So anything with an eccentricity of 0 is a circular orbit. In practice, it's actually very hard to get an exact circle. So you might find orbits have an eccentricity of 0.001. Essentially, that's a circular orbit, but not exactly. So anything less than 1 and greater than 0 is an ellipse. There are special cases that are equal to 1 and greater to 1. So we'll talk a little bit more about that. I already kind of mentioned this, that an eccentricity of 0 means it's circular. So an eccentricity of 1 means it's a parabola. It has a specific, special kind of trajectory. And then an eccentricity greater than 1 is a hyperbola. So think about Voyager or space probes that we've sent to discover the planets. They're not coming back to Earth. They don't orbit the Earth. They may someday orbit the sun, but they probably will not. We'll never see them again. So anything with an eccentricity greater than 1 is something we'll probably never see again. If it has an eccentricity between 0 and 1, it's called a closed orbit. So let's look at, okay, so what does eccentricity, what do the different eccentricities look like? So here we have different colors, and here you can see, if you look at the numbers on the right, and the red corresponds to a circular orbit. And by the way, the Earth is at one of the foci here. And on the other end of the spectrum, it has the green, for lack of a better description, has an eccentricity of 0.74. Again, Earth is still at one of the foci for all these orbits. They're all in the same plane, and they all take, one thing that's important to note is they all take the same time to orbit. But eccentricity is really just one of the things that we need. So if we need to look, we want to look beyond eccentricity. So for example, here you see 2 different orbits, but they both have the same eccentricity. One is just bigger than the other. So we need to do more to describe the shape. So the other thing we look at is the Semimajor Axis. So recall that in orbital mechanics, it's important to know that we look at the radius rather than the diameter. So in orbital mechanics, that's why we look at the Semimajor Axis. We don't really look at the semi-minor axis. So the Semimajor Axis A is the other key component. One thing to remember, and I think I've already mentioned this, is that Earth, if it's orbiting Earth, Earth is always at one of the foci. If something is orbiting Mars or something is orbiting the Sun, so for example, the Earth orbits the Sun is at one of the foci of Earth's orbit around the Sun. Earth's orbit is not exactly circular, it is slightly elliptical also. So important things to know about the orbit. So some definitions that you're going to need to know. And you will need to know these. So when we have Earth at one of the foci, the closest point, which you see, is called perigee. And the other side, the opposite side, the farthest point away from Earth, or the orbiting body, is called apogee. And it's important to note that, whoops, sorry about that, the G-E-E suffix indicates that satellite or the orbit that you're talking about is Earth. So for example, if we were to talk about something orbiting the Sun, for example, the Earth, we would talk about its perihelion. So helio or helion is the suffix that would tell you we're talking about an orbit around the Sun. The general term is apoapsis and periapsis. And again, for the special case of a circular orbit, apogee and perigee are one and the same. So let's take a look at the period, if you will. So the period is how long it takes something to orbit. We always can, if we are given, for example, the time to orbit. Here's ultimately the equation, and here's what you need to know. So t is the time; it's the orbital period. 2 pi is a constant. A is the Semimajor Axis, and notice it has kind of a funky exponent. Mu is called the gravitational parameter, and it's equal to the gravitational constant, which you probably remember from physics, and m. We use a large M to indicate the central body that satellite is orbiting. So in this case, it would be Earth. So let's take a look at this a little bit. 2 pi is a constant. G is a constant, M is a constant. So time totally depends on the Semimajor Axis. It's kind of interesting to note that this relates to, and we'll talk about it again at the end, Kepler's third law, which says that the square of the period of a sun's planet, or I'm sorry, of a planet is proportional to the cube of its mean distance from the sun. And that's kind of how we came up with this. Those words are kind of confusing, so I will show you a graphic later about what that means. So let's take a look at that in action. So we have circular orbits. They all started in the same place at 3 o'clock. And here's just a slightly different view. So you'll notice that the inner orbits go faster. They complete one revolution or a period. They have a period, it's called T, which is faster than the outer orbits. So it's kind of weird to think about, but when you are in space and you want to change orbits, sometimes you have to slow down to speed up. So if I'm in an outer orbit, if I'm in this outer orbit, I actually have to slow down to fall closer to Earth to speed up. Kind of a weird thing about orbital mechanics. So here's a view. So we know now about eccentricity, and we know about the Semimajor Axis, A. But here we know that we need to define some other things. So all of these orbits here have the same eccentricity and the same Semimajor Axis, so they have the same period, but they're different. So what's different about them is their inclination. So we need 3 more things to describe a satellite's orientation in space, if you will. So we're going to look at these things right here. One is called inclination. The other is called right ascension of the ascending node. So it's RAAN is commonly how that's written, and it has a symbol. We'll get to that in part 2. So as you look at this diagram, you see a red arrow. We'll talk about that. But also notice the grid. So that grid is the equatorial plane. So here's the definition. This is a really good slide about the definition of inclination. So again, on the right hand side, you see some different numbers. Inclination is denoted by just simply the letter I. So inclination is really just the angle between the equatorial plane, and you see the grid here, and the plane of the orbit. So as measured from the equatorial plane. So for example, the yellow orbit, inclination is 5, and then the most extreme, if I could call it that, is the orange orbit with an inclination of 75 degrees. So let's take a look. So notice that they have the same E and A. They have the same eccentricity and semimajor axis, but they have different inclinations. So they all have the same periods. There is no assessment, but you will, if you're watching this on Edpuzzle, you will have already done so. This completes part 1.